Example, the data show the chest size and weight of several randomly selected bears. Let chest size be the independent variable x and determine if there is a linear relationship between bear chest size and weight by conducting a t-test for the slope. Assume bear chest size and weight are normally distributed variables. So if we look at the data in the table, we can see that there were 6 bears. And for each bear, we have 2 quantitative measurements. So for the first bear, the chest size of the bear was 47 inches. And for that same bear, the bear weighed 457 pounds. Okay. And for the second bear, the chest size was 46 inches, and that same second bear weighed 496 pounds. So step 1, let's state the null and alternative hypotheses. For linear regression, your null hypothesis will always be that there is no linear relationship. So nothing's going on, there's no relationship between bear chest size and weight. The alternative hypothesis is that there is a linear relationship between the 2 variables, so between bear chest size and weight. For step 2, we want to check the requirements and verify we can reliably use the t-test for slope, and we also want to calculate the linear correlation coefficient R. In order to do these things, I am going to rely on StatCrunch. So I'm going to go back up to my data and I'm going to copy and paste it. And here I am in StatCrunch and I'm just going to paste the data. I go to stat, regression, and simple linear. Remember that we are told to use chest size for the x variable. The y variable is the weight. That is all I need to select. I'm going to leave everything else the same. And I hit compute. Here's the readout. And let's take a look at a couple of things here. First of all, I see that R, which in StatCrunch it's capital R, but the linear correlation coefficient is 0.929 ... That indicates that there's a fairly strong linear relationship in the sample data. Okay, remember that's not the population, that is corresponding to the sample data, does indicate a fairly strong linear relationship. I am also going to confirm this by looking at the scatter plot. And here, if we look at the scatter plot, we see a point here. There's 1 bear, 2, 3, 4, 5, 6. And they do indeed seem to follow a linear pattern, just visually inspecting what I see here. So let's just summarize that the requirements are met. We were told that the sample was randomly selected 6 bears. Visual inspection of the scatter plot confirms that the points approximate a straight line. Also, the linear correlation coefficient R was approximately 0.93, indicating a strong linear relationship in the sample. There are no extreme outliers that are known to be errors. Before we move on, I want to be really clear about what we're going to be testing by running the, calculating the p-value and doing the t-test for the slope. We will test whether there is evidence that the strong linear relationship that was observed between bear chest size and weight in the sample also exists in the general population. Okay, step 3, we're going to state the p-value of the test and interpret it. So moving back to StatCrunch here and clicking on the bottom arrow, I can take a look at this guy. I'm going to make it a little bigger so you can see. But I'm going to be looking at the p-value for the slope. And the p-value for the slope is 0.0074. So that's a pretty small p-value. So to summarize, the p-value of the test is 0.0074. A p-value of 74/10,000ths means it would be quite unlikely, a less than 1% chance, to get data like those observed if there is no relationship between bear chest size and bear weight. Step 4, let's draw our final conclusions. So my conclusion, since the p-value of 74/10,000ths is less than 0.05, this tells us that the data is quite surprising if there truly is no linear relationship between chest size and weight. Therefore, we reject H naught and we conclude that there is a significant strong linear relationship between bear chest size and bear weight in the general population. Before we move on, I just want to note that R, which is approximately 93 hundredths, indicates that there is a fairly strong linear relationship in the sample, while the p-value of 74 ten-thousandths tells us that these sample data provide strong evidence that this same strong linear relationship can be generalized or inferred for the whole population of bears. One last question. Since there is evidence of a linear relationship in the population, use the regression line to find the best predicted weight of a bear with a chest size of 44 inches. And after you find the best predicted weight, in this case, how would your answer change if the p-value had been greater than 5/100ths? In order to answer this question, we first, recall that there was evidence of a linear relationship in the population. This means that the regression line is a good model for my data, and I can actually use it to make predictions. Okay, so going back to StatCrunch, if I look at the StatCrunch readout, the first page, I see the equation of the regression line. Just to recap, from StatCrunch, we found the regression line was W equal negative this number plus this number times C. So of course W is the weight and C is the chest size. Therefore, the best predicted weight of a bear with a chest size of 44 inches is, and all I did here was I just plugged 44 into my line. And the answer I got was 461.67, which rounds to 462 pounds. This only works when there's a linear relationship, so you have a low p-value. So what would happen in the case where the p-value was greater than 0.05 and we did not have evidence of a linear relationship in the population? In the case that the p-value is larger than 5/100ths, we would not have sufficient evidence of a linear relationship, so we would not use the regression line to make predictions. Instead, we use the mean of the bear's weights. So in that case, I would add up the 6 weights, divide by 6, and this would be my best prediction for a bear having a chest size of 44 inches.